Okay, so as usual, with this CHEM102, just to be sure you're in the right place. And lots of handouts the first time. What you'll notice is unique for this first handout is my schedule. So that shows you where I am and when I'm there. And there's also a handout for tutoring, free tutoring. Barry Pine is doing tutoring in the summer. So if you run into trouble and you can't get in touch with me, you can Zoom a tutoring session with Barry. That's provided by the college free of charge. Then you have the syllabus, and you have chapter 10, chapter 11 PowerPoints, and come in and sign in and grab handouts. We also have the review documents that I prepare for each chapter. Yeah, sign in. And the review documents are set up to look like exams so that you get a feel for what to expect. And there's a key in Brightspace. I don't print the key out anymore. I used to, and I broke the printer. So I don't do that anymore. And if the key doesn't help you with questions that give you trouble, then there's also handwritten work problems.
Do I have to grab one of each? Or?
Yeah, one of each. Yep. And then if that still doesn't flip the light switch for you, then bring the ones that are giving you trouble to our review sessions. Unless you want to connect with me. And then since it's summer, I don't have regular office hours, but you can, in the syllabus, you'll see my cell phone number. You can text me if you need help. That's the best way to do it. And then we've got extra credits or crossword puzzles. The crossword puzzles are vocabulary reinforcement. And I take all the grades that you get on the crossword puzzles, average them together, and that's worth one exam, extra credit. Okay, that's the handouts. Now, is everybody, well, I know you guys are, but the newbies, are you familiar with Brightspace? You know how to get into the class? Okay. You need to be able to get into the, let me go back. Let's go back here, I think. My home. There. Nope, that's not it. So I better go backwards. See if it'll do it this way. Go to the New River landing page. Here we go. And then click on My New River. And since I've already logged in once, it's going to take me straight to this page with all the icons on it. It'll ask you the first time you log in your login ID and your password. So you should have been given a password. Even transient students get passwords, so you can get into the system. If you don't have one, if you don't know what to do, then contact our help desk. Call the help desk and they'll fix you up. But once you get in here, then you're going to have fewer icons than I am, I'm sure. But you look for the D2L, that's Brightspace. That's the learning management system. And all the courses that you're registered in should show up down here. If they don't, go up here to this waffle. And it drops down all your courses. So then that it's the ones that are down here below are the most recent ones that you've accessed. So you may have to go to the waffle first to get them in the system. So here's 102. And the reason I'm going here rather than just putting the syllabus up there is because the syllabus is in here too. In fact, everything I hand you in person in class is duplicated in Brightspace, even though it's a traditional course and we're not dependent upon the learning management system for anything but grades. I duplicate everything in Brightspace, so if the dog eats your homework, you get another copy. Here's the also this is your free tutoring. I put that in there also in case you lose that copy. And I've had good reports from students that have used Berry Pine. Sometimes it's helpful to get another perspective. Um, if you rely on my presentation, it's kind of like the old monophonic sound. I'm old enough to remember that versus stereo or high fidelity or quadraphonic, surround sound. Right? This is if you get your information from one person, sometimes it just doesn't click. You need another perspective. Okay, so when you get in here, this is called this blue thing up here is called the mini bar, and that's how you access different parts of the course. If you want to contact me or anybody else by email, click the class list, and you go in here and you can click up here like that, highlight everybody. You can send everybody the same email, or you can click individuals. Like if you just want to send me an email, just click me and go up here and say email. You can send emails from here till the cows come home, but you can't receive them here. You have to go into your assigned New River address, your email address. Does everybody know what it is? You guys can sit back and relax for a few minutes. Okay, good. Because that's how I communicate in class and by email. So if I have some announcement to make or some change in the scheduling, I'll send it to you by email. So it's a good idea to check your email at least once a day. Okay. Everything else, you can go into assignments, and these are just things these do not include exams. If you have exams that are allowed in Brightspace, then you have to go over here to more and click quizzes. But assignments are like extra credit crosswords. I think that's all we have in here. Yeah, extra credit crosswords. If you want to see your grade, current grade, then you go into grades. And it's not going to look like, maybe why don't I do this as a student? How about that? It may look more familiar that way. Then you go into grades, and it's going to show up all the assignments, all the possible grades here. And there's one thing that I've never liked about learning management systems is the grade book, the way the grade book calculates averages and grades. It's just, it's always clunky, right? It's not flexible. So I take all of the grades that we accumulate through the semester and put them in my spreadsheet, an Excel spreadsheet that I've created so that I can modify the grading scheme the way I want. And then the average that comes out of that, based upon the syllabus reported way that we grade, we'll look at that in just a minute. Then I put that in as a manual current grade. So if you see a value in there for your current grade and you've submitted something that you think should have gone into that grade, but the grade is not listed down here, that means it's not averaged in yet. So don't panic. It may take me a day or two to get around to it. So there, and the exams, since the exams are face-to-face most often, and I'll talk about that in a minute also. I put those in. If you take them in class, I'll grade them before you leave the class, so you'll know where you stand. Homework is through Cengage, and it's called OWL. That's their name for it. And these are your extra credits. Okay. So everything else, if you want to find anything that we've done in class, duplicated in Brightspace, or any assignments that you might have missed. Say you are absent one day, you didn't get the handouts. They're right here. So you can go to, let's see. Yeah, start here, lessons and resources. That's where I would click. And then if it's not already expanded, it'll expand everything down this left-hand column. And you can go to, here's your homework links and registration. So when you get your textbook and you get the code, you go in here and click this, and it'll take you to the Cengage website where you do your homework eventually. Now, it's not going to let me go through like you would go through because it knows I'm an instructor, even though I've got my learning management system set up to look like a student. It's still going to it's going to know that I'm an instructor, so it's not going to treat me the same way it would you. But you need to have an access code. And then if you've never been in to Cengage and created an account, it'll ask you to create an account too. After that, you won't have to do it anymore. It'll know it's you. Once you go in, if you enter through the learning management system, it knows, it recognizes you. So that simplifies things a lot. Okay. There's another nice thing that these publishers are doing is they give you 2 or 3 weeks, depending on the publisher, of free access. So while you're trying to get your textbook and your access code, you can go in and register with free access, and then they give you a couple of weeks to get your paid subscription, and then you can go in and put that in, and from then on you're free to fly. Okay, so that temporary access would probably be where you do that, but it saves everything. Even since you've come in through the learning management system, it recognizes you and it saves your work. So when you get your access code and you've got permanent access, then it remembers all the work you've done, so you don't lose anything. Okay, so that's your homework, and the homework is due the same time as you take your exams. By midnight on that day, when your exams are due, is when your homework is also due. That simplifies things for me and for you. Okay, so let's go back over to, let's see here. You'll notice that occasionally you'll find the breadcrumbs up here at the top, right along there. And that makes it easier to go backwards if you want to go back to homework links and registration. Now you can, once you're in the system, you can go to that link and do the chapter homeworks that way. Or you can go into the individual modules for each exam, and I've got links in there for the chapters. So that just saves you a step or two getting to the homework that's for that exam. You can do it either way. We've got videos here provided by Cengage to help you understand the registration process, how you do assignments. This Chem Doodle might be useful in case you ever have to create a chemical equation or a formula of some kind, and Chem Doodle is the tool that they use. So this gives you some practice and some ideas. I'm not sure. I haven't used it in a while. Is it any good? Did you guys use it? No. Okay. Just okay. Never mind. Okay. So that's how you get to your homework, and then let's see. Oh, that's duplicated. Okay, so that's the same stuff as the one I just showed you. That's not right. That's not the correct schedule. Right, that's last semester. That's last summer. All right, so when in doubt, go back to the syllabus. That's the contract. If there are any mistakes in the learning management system, then default to the hard copy. Okay. And then tell me about it so I can fix it. But I need to get rid of this. Since I'm in here as a student now, I can't fix it. But I will delete that one and put in the, well, that is the right one. Yeah, that is the right one. I didn't realize I'd done that already. The reason I know is because there's June 19th, which is also called Juneteenth. We don't know if that's a holiday yet because the governor hadn't said, but I inserted that holiday in there just in case. Now, if the governor doesn't pronounce that as a state holiday, then we'll meet on that day and we'll have class exercises. And I've created another and modified an alternate schedule that once I know whether it's going to be a holiday or not, then I'll give you that schedule. Okay. And I just shifted some things up into that spot so that we wouldn't waste any time. But as it stands now, I've set that aside. Well, since we're here already, this is a good place to talk about the schedule. Today, after we do class business, we're going to get through 2 chapters. We have to. There's no ifs, ands, or buts about it. We got to get through chapter 10 and 11 today as a lecture. And then next Thursday, this is Tuesday. Yeah, Thursday, we'll do a review on those chapters. And I work from the review documents for those chapters. And then we probably won't have time to talk about the lab today, but we will have lab time scheduled for Thursday, and I'll use that to introduce you to procedures. And you guys can relax. But since we got 3 newbies, I need to do this. Okay, so I've highlighted those where something's due. Homework, exam, you can see it's highlighted in yellow. And then I've grayed out days when you're not actually meeting, but they're interesting, they're useful information. Like on that Monday, June 30th, that's the mid-semester grades are due for the 10-week term. So everything before that that's graded before that will go into that value that I report to the registrar. And that gives you an idea of midterm, how you're doing in the course. I would, if it was me, every day or two, I'd go in and check my grades, just to see if your instructor's on the ball. Independence Day is a holiday, but it doesn't affect us. And the last day to withdraw with a W for the course is July 18th. And then we'll have, we will have time to do a review before the final exam. So that's good. All right, let's see. The syllabus is where? Here we go, syllabus. So there's a copy of the syllabus, there's my schedule, and this is how you connect with me for office hours, but since I don't have office hours, I still use this connection. If we set up a meeting, right, a Zoom meeting, then this is how you'll get to it. Just click on that and open the meeting, and I'll be there when we've agreed upon time. Okay, so let me go back. And there's my schedule. You have a copy of my schedule. It's duplicated there. Here's a duplicate of the syllabus. Now, things about the syllabus. Let's see. Most important things are the textbook right there. And if you're only going to be with us for the summer, then I just buy the 1 semester version. If you're going to use Cengage in any other course, which is unlikely in the summer, but if you go back to your, since your transients go back to your college and they use Cengage products, then you may already have an account with them. I don't know. I don't know. Some universities, they may still do this. Professors are very territorial, and they like to create their own textbooks. I remember several courses I had to take as a student. We bought the instructor's textbook because it was required. I don't want to have to write a textbook. I can correct errors in textbooks, but I don't want to have to write one from scratch. If you want to, the access to the Cengage course, the homework also gives you access to the textbook, the electronic version. And in fact, Cengage Unlimited gives you access to any title in their inventory. So if you have more than one class, you get the whole shebang, just one price. If you want a hard copy, I'm old school. I like hard copies. You can buy a used copy, and there are the particulars for this version, which is 10th edition. Used copies, you should be able to get them pretty cheap online if you want a hard copy. If you don't, if you're happy with electronic versions, that's fine. And it's nice, you can search them. Can't do that with a hard copy. Those student learning outcomes, you can read those at your leisure. These are New River outcomes. They used to call them general education outcomes. Those are really for me, right? And any of you who are interested. Here's the grading scheme. All right, so chapter exams, take all the chapter exams, average them together, and they're worth 54% of your grade. So say if you get 100 on every exam, average them together, that would be 100%, and the 54% would go into the average. So 54 plus whatever you get from the others. Let's say you're perfect and you got 100% on everything. Then I would take 54%, add that to 16, add that to 20 for the homework, add that 10 for the attendance. And then any extra credit is on top of that. Okay, let's see. This is required stuff we have to put in the syllabus. Course materials, everybody needs a calculator. I mean, a bona fide calculator. No smartphones for exams. You can use your smartphone calculator anytime you want, except exams. Because smartphones are just way too smart. So during exams, you have to have a calculator. And you got to learn how to use it, right? We don't have time to teach you how to use it. I have on occasion helped students find things on their calculator, but we're not going to carve out time from the class to learn how to work a calculator. Most calculators, I think now everybody gets are algebraic, like 1 + 1 =. Right? I've got one of those spares, right? But the one I use is reverse Polish notation, which takes some getting used to, but once you learn how to use it, it's a whole lot faster than the algebraics. And if you don't have a calculator and you need to buy one, just look for scientific on the package. If it says scientific, you'll have everything you need. Everything else I hand out in class for the lecture. We'll talk about the lab later. So those are the only things you need. Your whatever you would like to write on. If you take notes on your computer, that's fine. I hand out hard copies, you notice, of the slide sets, and you can scribble on those, or you can call them up on your laptops, and that's perfectly all right. That's the general course outline. We have regular exams, we have homework, right? We've talked about those. I give you credit for attending. If we don't have an exam, if we don't have a lab on that day, which are very few this semester because it's compressed. But on those days when we don't have an exam, a lab, you can zoom in and you'll be counted present. You miss the opportunity to pick up handouts, of course, but since they're in Brightspace, you can print your own copies if you want. The bonus exams, some exams have bonus questions on them, right? So you can add some points there. And then, of course, we have the crossword puzzles, and there'll be crossword puzzles for every chapter. I think 14 and 15 are combined because both of those chapters are acids and bases. I just put them together into one crossword. Let's see. There's the schedule again. What else do we have? I get a little blurb on artificial intelligence. That's probably not going to be an issue for the lecture course, but for the labs, artificial intelligence, it can be useful, right? It can help you clean up your language. It can give you a starting point if you're writing a formal lab report. Give it the information and have it construct a paragraph for you. And that's okay as long as you go back and you better read it first and be sure it makes sense, because artificial intelligence may be artificial, but it carries with it the same weaknesses as humans do. In fact, some artificial intelligence programs have been identified as psychotic by professional psychiatrists and psychologists. And sometimes if the program doesn't have enough information to create the product, it'll just make stuff up. So you need to go back and read it if you're going to use artificial intelligence. Read the product and see if it fits what you need. We'll talk a little bit more about that when we get to lab discussions. Now, New River policy for attendance. You can have excused absences that I report to the registrar in our system. But since I'm giving you credit for attendance, if you don't attend, I mark you absent. No ifs, ands, or buts. It doesn't matter if you're sick. It doesn't matter if grandma's died. That one crops up every semester. So I don't know if it's true or not. As far as the class policy is, if you don't show up by some acceptable way, then you're absent. Okay, and you don't get credit for that in that 10% sliver that goes into your course average. Makeup testing, we can do that. It's going to be even more difficult since we're only here for 10 weeks to do it face-to-face. So the option for that is Brightspace. Makeup testing would be through Brightspace more than likely. And in that case, if you take an exam in Brightspace, you need to be comfortable with Lockdown Browser and Respondus Monitor. Does anybody use that? Okay, good, good. We don't have to beat that horse. Let's see. If you think I made a mistake in your grading an exam in particular, just call my attention to it before you leave class, because I'm going to grade it before you go. If you take the exam in Brightspace and you think I made an error, then it'll take a little longer to correct the problem. And I'll look to see if I've made an error. Most of these exams, the questions I use, I've vetted them pretty well. So it's unlikely at this stage in my career that you're going to find an error in the exam, in a question. But it can happen. If I make a mistake in a key, and then, or I've had students say to bring a question to me, and it's, there are two possible answers in this multiple choice. That has happened. And in which case, once I look at it and say, yeah, you're right, then I'll give you credit for your answer if it's one of those. Everybody knows how to be a good citizen during exams. And let's see, what else? Outside class, we talked about that, how to get in touch with me. Everything that happens in class is recorded. So I'm on camera right now, and I'm sharing the documents I share are being recorded through Zoom. And what I'll do is at the end of the class, I'll take the recordings and I'll process them in my video program, splice them together so that you'll have this part on one side and you'll have the slides or whatever else we're doing on another part. And you can go back and review if you want to do that. Let's see, they're my office hours. We should be getting close to the end. This is homework. That gives you an idea of how the homework works. Let's see. Exam and attend class in Zoom. If you, I've had students attend class in their cars while they're driving. I wouldn't advise it, but if you have something to hold your phone and the camera can pick you up, then if you're proficient with your smartphone and you can click that one link, this link right here in blue, that way, if you can, and if it's in the document, control click usually works. It's got the password built in. The passcode is built in. But if you have to go through your Zoom app and join a meeting, then here's the meeting ID and here's the passcode. You can do it that way. Okay. Last word. If I give you permission to take the exam in Brightspace, then consider it, do the exam as if you were sitting here in class, and you wouldn't come to class in your underwear or your gym shorts or your pajamas, right? So if you're on camera, everything that the camera sees needs to be street clothes, okay? So you don't need to be doing it in bed either. Sit up at a table and take the exam like a normal person. Okay. Let's see. Stop me anytime if you have questions. Okay. I don't mind. That's one of the reasons I have hard copies, slide sets, and everything, so that if I digress or if someone asks questions, I can go back to where I was. I don't have to remember. Okay. Let's see. Any more? Oh, we haven't done the modules yet. Okay, so the learning modules are right here. Oh, Zoom class meeting. If you zoom in, you click on this one and just hit that link, and it should bring you into the class. Learning modules. So they're organized by exams. So we have 7 learning modules, and that covers the chapter exams. I don't have a learning module for the final exam. What we do for review there is I've compiled all the previous review documents into one, and I've picked out questions. And if you are having problems with one particular type of question, bring that to class. We'll do those first. I only select the ones like that, so if nobody has any questions, we'll have something to do. And then, of course, while we're going through the review, if something just say, uh-oh, I need to know about this, stop me. Cover your problem first. Okay. Okay, so each learning module is going to look similar. And we'll have, if it's too busy, just hit this collapse all, and then you can go down and open whichever ones you want. This is a checklist that I created for each one. This shows you what you should be doing for this particular module. So read the textbook, obviously. View the video lecture if you're not home, if you're not here in person, or if you want to review, then you need to look at the videos. There's your homework. Work the problems in the review document. These are not graded. These are just for you. Right? So these are to give you practice, and you'll know, have a feel for what type of questions I'm going to ask. Okay. And to check yourself to see if you know the material. So working those problems in the review document is up to you. If you're limited on time, just go through and work every other one, right? Because there's lots of repetition in there, right? Okay. Only if you have time, then work as many as you can. In fact, you may already know this. The way you learn chemistry is to work problems. This lecture is just the tip of the iceberg. Right? Working problems, the problem solution gives you different angles to approach the concepts that we learn and how to use them to solve real world problems. So work as many problems as you can get your hands on and you have time for. And then the crossword puzzles, right? This reminds you that those are extra credit, and then the exam. So there's your checklist. And these are previous semester lecture links. What they'll do is they'll take you to YouTube. That's where I store all my videos, on my YouTube channel. And this will take you directly to that one. So I'm not going to waste your time with that now. The only bad thing about it is, since it's free service, you have to sit through commercials. Right? Or I don't know, can you fast forward through them, or they force you? No, they force you to watch them. Okay, so you can get up, go get a drink, or use the restroom during the commercials. Under the chapter, the Zoom doll chapter tabs, you'll find PowerPoints, duplicated PowerPoints, review document. This is where you'll find your key. Right? If you open that up, there's your key. So it's answer key for the review document. And another copy of worked problems, and then any extra documents or links are also located here. So this particular one, how to find the edge length of a body-centered cubic, is, I think it's the second one over here. So when you go into this particular, excuse me, part of the module, all right, force go back the hard way. Good to be indoors right now. Where's my modules? Here they are. So they're all going to look the same. Right, when you go into these chapters, let's see, chapter 10, that's going to be your PowerPoints and related documents. So chapter 10, chapter 11 is going to look the same, and you're going to have your lecture videos here. We have review videos also. As long as we do a review in this room, it'll be recorded. I don't record lab activities. And it's kind of hard to do that because everybody's scattered everywhere. But if I do an introductory presentation for a lab in here, it'll be recorded, and I'll post it in 104. Did we lose somebody? No, that's okay. Might have dropped out and come back in. Okay. I know I'm taking too much time. There's your crosswords. Let's see, what's chapter 12? 10, 11. What's chapter 12 doing down there? Oh, that's a separate module. Yeah, that's the next module. Sorry. So they all follow the same format. And if you have, there are also archived videos, right, of previous recordings. And you don't have to go into those unless you want to go back in time. Sometimes I have self-help videos. And if I give you permission to, if I open up an exam in Brightspace for you, then you'll have useful information. And if you look at your one of your review documents, there should be at the back useful information. Already here. Useful information about constant values, formulas. The formulas won't be named, but you need to be able to recognize, but they're there. And any other extra information you need, like this one has polyatomic ions, right? Unless you have them memorized already. I don't know if you're coming from a more rigorous first semester, you may have to have already memorized them. And then the periodic table. Anything that's useful information in the review document will be available for exams. You just need to learn how to use them. And if you take the exam in Brightspace, then here's your useful information. Then you need to print that out or get it out of here somehow, because once you enter the exam, lockdown browser won't let you do anything else. It won't let you access this information. So useful information, periodic table, you need to keep those, get those first. Then when you go into the exam, see, it's not authorized yet. So the exam link is not there because as a student, I haven't authorized myself. And there's chapter 12 crossword. Okay. One other thing, if you have an assignment that's due on a certain day, say a crossword puzzle, you can bring it to class on that day, the exam day, or you can give it to me earlier if you want. But you also have till midnight that day to submit it. So if you forget, you walk out the house, you've got too many things on your mind, you forget to bring it to class, then you have till midnight. And this is where you submit it, right? You just go in here and click chapter 12 crossword. And this is the same thing for lab reports. Right? Do the same way. And you'll notice down here an upload link right there. That's where you would upload your document. Right? If you do it by hand, then you'll have to take a picture of it and submit that here. Okay. That's learning modules. I think we've covered everything, and I've used up 45 minutes of our class time. Let's see. Supplemental documents, they're just that, supplemental. You can take them or leave them. And if it was me, I'd explore, just see what all is in here. Otherwise, I can stop this share and go to our first chapter, chapter 10. So let me share chapter 10 right here. There it is. Okay, let's make a slideshow out of it. Let's see. I'm going to have to try to not to talk so much to get through all of this. Come on. There it is. There's my slideshow. Okay. So, not sure. We should have, you guys, first semester should have covered certain basic topics. In chemistry. And now we're gonna go into more depth. In this first one, we're talking about characterizing liquids and solids. And our focus is going to be on how liquids and solids constitute themselves. In other words, is there some type of bonding force that holds them together? Well, that's a rhetorical question. There has to be. If there was no force holding a liquid together, then it would be a gas, right? So we differentiate between what we call intramolecular bonds and intermolecular bonds. The intra means within the molecule. So these are bonds that we've already been introduced to in first semester chemistry. They can either be ionic bonds, right? They can be covalent bonds, or they can be somewhere in between. Those hold the molecules together. Excuse me. When you get two or more molecules, and for simplicity's sake, we're going to discuss these forces in terms of covalent compounds. It makes more sense that way. Ionic compounds are really, they're kind of ionic networks, right? Positive, negative, negative. They're huge structures of positives and negatives. So this discussion makes more sense in terms of covalent compounds. So we have the intramolecular forces holding the molecules together, and then we have potential forces between molecules that produce the different phases, solids, liquids, gases. Now, these forces can be characterized as depending on whether the molecule has a dipole. We did discuss that, didn't we? Yeah, dipoles. In other words, are the molecules polar? Do they have an uneven distribution of electrical charge? So conceptually, we would say something like this. This end would be positive, that end would be negative as a dipole. And the strength, the degree of separation of those charges can be very small, or can be very large. So this dipole, and I use water as an example. Right, there's your water molecule. And the electronegativity, we have covered that, right? Electronegativity of oxygen is much greater than hydrogen. So we get a bond dipole in the direction of oxygen. In other words, it's going to be slightly negative, and this end's going to be slightly positive. Let's see, I better balance it. Okay, so that gives you an overall dipole for this molecule in that direction. This shows you the positive end, this shows you the negative end. When those molecules encounter one another, say it's a pure substance, nothing but water. When they encounter one another, they orient themselves so that you get the negative end here, close to the positive, and you get a weak attraction. Well, a strong or a weak, depending on the molecules. That's a dipole-dipole force or interaction. Okay? Now, this particular dipole is special because this is known as a hydrogen bond. So when you have either oxygen, I think, nitrogen, or fluorine attached to a hydrogen, like that, and it can be anything else out here, then you have the potential for a very, very large dipole moment in this molecule. Okay? That gives you the potential for a very strong dipole-dipole interaction called a hydrogen bond. These hydrogen bonds are very strong. That's why water is a liquid at ambient temperature and pressure on the surface of the earth. It's not a gas. If it wasn't for that, it would be a gas and we'd be in big trouble. Any other molecules that have a slight separation of charges will exhibit a dipole-dipole interaction. Weaker ones like, let's see, what would be an example? Let's see, sulfur dioxide, right? So you'd have, let's see, probably slightly this way. So your negatives would be on this end, your positives would be on that end, and you could set up an interaction between the next molecule like that. That would be a dipole-dipole interaction. Now, there are some molecules that don't have dipole. Like the diatomic elements, like oxygen or nitrogen, like examples. Those don't have dipoles because the atoms on either side of the bond are equivalent. There's no equal separation of charge. But we know that they form liquids. Right? We do that. I mean, that's industrially, we do it all the time. Right? Rockets now go up with liquid oxygen in one of their tanks. Right? How do you make a liquid? Well, you cool it and you compress it. Right? You get those molecules close together and you reduce their temperature, right, so that they condense into liquids. Now, why do they condense into liquids? There has to be some force between them, holds them together. Right? That's an attractive force that makes the liquid. So how do you get these two molecules to attract one another, right? If there's no separation of charge. Well, in fact, there is a separation of charge, only it's temporary. The dipole that we talked about earlier is permanent. But you also have possibility of temporary uneven distribution of charge because electrons are not static. They're not just sitting there. They're in constant motion. So there's the possibility with this molecule for, say, we get slightly negative on that side. That means this side is slightly positive. Right? What does that do to a molecule that's close to it? Well, these negatives push those away, these electrons away. That makes this side slightly negative and that side. Just for an instant, split second, like microsecond. And in that amount of time, you get an attraction between the positives and negatives. That's called a London dispersion force. It's called dispersion because the electron cloud is dispersed unevenly. And London, of course, is the name of the scientist who came up with the concept. So these are temporary. The dipole-dipole interactions are permanent. And you can also get dipole-ion interactions. Say if you have water molecule, you have a pure water, and you add sodium chloride to it. All right? Yeah. Which end is sodium going to be attracted to? Yeah. So you can have ion dipole interactions too. That's what makes sodium chloride soluble. Okay. So we defined some terms. Now, the last point I want to make is in the form of a question. Which is stronger, the intramolecular bonds or the intermolecular bonds? You can think about this logically too. What would happen if the intermolecular bonds were stronger than intramolecular bonds? They would rip the molecules apart, right? So the intramolecular bonds within the molecule must be stronger than the intermolecular bonds that hold molecules together. They have to be. You don't have any choice. Some things in the sciences are logical, and that's one of them. Now, we can measure these forces, right, and confirm that that logical conclusion is correct. Okay, we talked about hydrogen bonding already. It's the strongest of the intermolecular forces. Okay. Intramolecular bonds are stronger than intermolecular bonds. And there's your explanation in blue and white. Okay, so when a substance changes from solid to liquid or from liquid to gas, the molecules remain intact. It's still, if it's a pure substance before, it's a pure substance after. And these changes in state depend upon the forces that are attracting those molecules to each other. Now, since the forces are weaker than the intramolecular forces, then it takes less energy to go from solid to liquid to gas than it does to break the molecule apart. But you still have to add energy. Think in terms of energy balance. If we go from a solid to a liquid, we're going from an ordered state to a less ordered state where the molecules have the opportunity to slide past one another. Think about that in terms of the characteristics of a solid. It has a definite shape and a definite volume, whereas the liquid has a definite shape, an indefinite shape, but still a definite volume. Why is that? Because the molecules can move past one another. They're not locked in place so that you can't sit them on a table and they'll maintain their shape. You have to put them in a vessel because they can move past one another. Why can they do that? Because they have more energy now than they did as a solid. And they're able to loosen those intermolecular bonds that would hold them in the solid state. Okay. And there's the artist's idea of your publisher's idea of illustration. Notice that the solid and the liquid are roughly the same volume. The liquid typically takes up a little bit more volume because you are creating more space between the molecules so they can move past one another. There's one exception that I can think of, and that's water. Think of this in terms of density also. Remember our definition for density? Mass per unit volume. If you have the same mass before and after the phase change, and the volume gets bigger, what happens to the density? Go down. It's lower density. So liquids typically have lower density than the solids, except for water. Water is a special case. Water, the solid, is less dense than the liquid. That's why ice floats. Right? And it's a good thing it does. Right? If ice didn't float, if it became more dense as it became a solid, it would sink in the oceans and the lakes. And once it did that, air temperature would freeze some more of it. It would sink. Eventually, all the lakes and oceans would be a solid block of ice, right? And we'd be in big trouble again. But as it turns out, everybody's seen a snowflake, right? How many points on a snowflake? 6. 6 points. It's hexagonal. Water gets together in this hexagonal form, like that. Then we have there, and then we have hydrogen here. Right? That means we would have like that, right? Our intermolecular forces there. And then we would have another hydrogen here and another hydrogen out there. And then over here, we would have, say, another oxygen. So that would be, right, with hydrogen here and hydrogen here. Well, what have we done? Well, in the liquid, the molecules can move past one another, right? But they're reasonably close together. But when they form the ice, when we form solid water, they do that. create all this empty space in there. And that empty space adds to the volume, which makes the density of ice go down instead of up. Okay. All right. So let me see, get back on track. When we go from liquid to gas, now we're going to an indefinite shape and an indefinite volume. So I've heard from childhood, a gas expands to fill the container, which is, it was true then, and it's true 70 years later. Because not only are the molecules able to move past one another, there's virtually no attraction between them, right? And lots of space, enormous amounts of space compared to the size of the molecule. That's why when we studied gas laws in the first semester, one gas was as good as another for the gas laws, you know, as long as they were behaving in an ideal region of temperature and pressure. And remember what that was? When does a real gas behave like an ideal gas? High temperature, low pressure. Right? And that's a relative term, right? High temperature relative to what? Well, absolute zero. 273 K is, actually, that's cold. 293 K would be room temperature. So that's high temperature. And low pressure is 1 atmosphere. So at these conditions, any gas will do, because it behaves as if the particles don't matter. The molecules don't matter. It's just the space that matters, because they're so far apart. And that's why when you put two or more gases together, you always get a homogeneous mixture, a solution, because there's plenty of space for everybody. And they don't interact much. There's some interaction, but not much. Okay. So those are characteristics of solids, liquids, and gases. And here it is in black and white. Right? So I don't have to spend a lot of time there because I've already talked about it. This is a demonstration of water behavior. Notice that the solid is less dense than the liquid. That's because of that behavior. Right? At what temperature is liquid water the densest? Right? The density will change with temperature, even for a liquid. Right? It's the most dense. Water has the highest density at 4 degrees Celsius. Anything below 4 degrees, now you're starting to get some organization toward the solid, and the density starts to decrease. Gases, of course, typically have very, very low density. We're using the same unit of measure here, grams per cubic centimeter, so that we can get a relative we can compare the densities of the different phases. But typically, when you look up the density of a gas, it's not going to be in grams per cubic centimeter. It's going to be in grams per cubic meter. Just so that you don't have to use lots of scientific notation. Okay, here are the dipole-dipole forces that we talked about before. And it's all electrostatic. In other words, separation of charge gives you negative, positive. Now, it's not a complete separation of charge. That would make an ion. But these intermolecular forces are electrostatic in nature. You've got a slight separation of charge, not a complete separation. You still got the polar bond, but the separation of charges gives you that ability to attract negatives and positives. Typically, the dipole-dipole force is about 1% as strong as the covalent or ionic bonds. And there's hydrogen bonding. Nitrogen, oxygen, fluorine, when it's attached to a hydrogen, let's use oxygen as an example. Anytime you have an OH on any molecule, anywhere in the molecule, can be water, can be ethanol, the drinking kind. Like that. Molecule would look like this. It would have the two hydrogens here. Then it would have an oxygen and a hydrogen there. So that methyl group out here. So that gives you the opportunity to form hydrogen bonds with that part of the molecule. Okay, so that the ethanol molecules can approach one another such that you can have the hydrogen on another ethanol molecule attracting like that, or you can have the oxygen on that. And one of the reasons, there are two reasons that hydrogen bonding is so strong. One is the electronegativity of these elements, nitrogen, oxygen, fluorine. Very high electronegativity. In fact, fluorine is the highest, 4.0. The other reason that the hydrogen bond is strong is because of the hydrogen itself. What is this? It's a proton, right? It's tiny. It's bound to the oxygen, but it's really tiny, so they can get close, really close to that charge. And remember, the strength of an electrostatic charge is based upon two things: the size of the charge and the distance between them. Right? So if you can get really close to that one with your negative charge, you can get a strong bond. Okay. And here, London dispersion forces, we talked about that earlier also. This is an instantaneous dipole, London dispersion force. And the other fact that should not be lost on you is that every molecule exhibits London dispersion forces, the potential for London dispersion forces. Every molecule, even the ones that have permanent dipoles. It's just that the London dispersion is so weak that if you have a permanent dipoles, then they don't matter, right? Which is stronger? Well, the dipole, obviously. It's hugely stronger than the London dispersion, so you can virtually ignore it. But if the dipole's not there, then the London dispersion is all you've got left to fall back on. Okay, I started to talk about this before, melting points and boiling points. The stronger the intermolecular force, the higher the melting point and the higher the boiling point. In other words, the stronger the forces that are holding these molecules together, the more energy it takes to get them apart. That means higher temperatures. Okay? And what we're trying to show here is let's see, how about, I'm just checking, I'm looking at each one. These are all hydrides. Hydrides of the elements in the periodic table in terms of groups, families, the verticals. So that top one, you'll see oxygen is at the top there with water. And then you go to the hydride of sulfur, then the hydride of selenium and tellurium. And notice that there's a trend as you go up from tellurium to selenium to sulfur, then the boiling point decreases. Yes, boiling point decreases until you get to water. And now you've introduced a new animal, hydrogen bond. Once you've got that hydrogen bond in there, water is no longer following the trend. The trend for water would go on that dotted line down to in the neighborhood of minus 80 degrees. Right? That would be the boiling point for water. Instead, the boiling point is 100 degrees Celsius, right? A distance of 180 degrees. That's quite a jump. And it's due largely to hydrogen bonding. You get some hydrogen bonding also with the halogens. So as we work our way up from iodine, bromine, chlorine, fluorine, you have a trend until you get to fluorine, and then you've got hydrogen bonding again. And that kicks the hydrogen fluoride up into a higher temperature range for its boiling point. Nitrogen is the same way. Right? So you get the hydrides of the nitrogen group from antimony, arsenic, phosphorus, and then when you get to nitrogen, you have ammonia, which gives you the hydrogen bonding ability again. But when we move over to the carbon group, you don't have the available hydrogen bonding for carbon that you did with nitrogen, oxygen, and fluorine. So it will follow the trend all the way from tin, germanium, silicon to carbon, all the way down. So the boiling point of carbon is very low, like 100, looks like about 165, minus 165 degrees. All right. So we got liquid oxygen in one tank in that rocket, and we got liquid methane in the other tank. Bring those together in the rocket engine, and off she goes. Within a day or two, I think the next Starship launch is due to take off. I think Starship 9, launch 9, should be within a few days. And Musk's Raptor engines use liquid methane and liquid oxygen for a couple of reasons. One is the energy density is pretty good. The other is methane burns cleaner than kerosene does. Right? Kerosene is what they use. Musk is still using that in his let's see, what are those? I can't remember the name of his rocket, that the workhorse rocket that he sends up usually from Cape Canaveral. Anyway, they use kerosene and oxygen there. Methane is better if you're going to reuse the engine because it doesn't produce a lot of soot, and it's less polluting too. Merlin engines are used on those rockets, but I can't remember the name of the rocket for some reason. Anyway, which molecule is capable of forming stronger intermolecular forces? Which one bonds with stronger forces? Right. Well, look at the molecule versus both of them have London dispersion forces, but water has hydrogen bonding. Nitrogen doesn't. So it's the weaker one. Water's the stronger one. Stronger forces are hydrogen bonded. There's your explanation. I used to use liquid nitrogen on a regular basis for one of my analytical instruments. We used it to flush out the optics. Right? It was more efficient than vacuum. Right? My spectrometer would detect vacuum lines in the spectrum of different elements. And if we had oxygen in there, then it would absorb those ultraviolet wavelengths in forms of ozone too. So the first instrument I had when I went to work for the USDA was a vacuum spectrometer. It would evacuate the space, and that was a problem because you get backstreaming of oil from your pump, and it eventually just coats your optics, and they're worthless. Right. So the next one we got had nitrogen flushing. So we just flushed the optics out with nitrogen, got rid of all the oxygen, and it was good to go. But Liquid nitrogen is at a temperature of minus 195 degrees Celsius. It's very cold. In fact, we use liquid nitrogen also to freeze plant samples. Freeze them quick. That way, they don't have time to undergo any degradation processes in the cells. Okay. The structure of the molecule makes all the difference. Here we have two examples of C2H6O. Okay. That's the molecular formula. Right? We learned last semester how to determine molecular formulas from the percent composition and the molecular weight. But we can draw this molecule in at least two different ways. One is the one I just showed you, right? The ethanol. Right? Or we can draw it as dimethyl ether. And you can count them up, see if we've got accounted for all of our atoms. Right? 2 carbons, 2, 4, 6 hydrogens, 1 oxygen, 6 hydrogens, 2 carbons, 1 oxygen. Okay. So it's the same molecular formula, but it's a different structure. Right? So which one would have the highest boiling point? There's your hydrogen bond. Ethanol has a much higher boiling point than dimethyl ether. Okay? Because this is a balanced molecule. It has no dipole. So the only thing it has available to it is London dispersion forces. Now, you would get a slight polar separation in here, this way. But there's something else to consider, is steric hindrance. In other words, you've got this big methyl group sitting out here and that one sitting out there. This may be slightly negative, but no other molecules can get at it, right? Because we got these big groups out here in the way, right? Take organic and you'll talk about steric hindrance till you're sick of it. Okay. Which gas would behave more ideally at the same conditions of pressure and temperature? Ideal behavior. Remember what ideal behavior in a gas is? Right. No attractive or repulsive forces. Okay. Or the conditions that negate these. Right? That's why we say high temperature. High temperature means these molecules are coming together at such high speed, they don't have the time or the energy to overcome the impact. So that negates those. Also, in this case, ideal behavior for the gas would be one in which the gas itself, the molecules themselves, don't contribute to attractive forces. So you have to know the structure. We already know nitrogen, like that. But how about carbon monoxide? You remember drawing carbon monoxide? Things like this. Carbon monoxide. You have a slight difference in electronegativity there, which gives you a dipole moment here. So this one would behave more ideally than that one because there are attractive forces available. Stronger attractive forces than this one. That's why we say more ideally at the same temperature and pressure. Okay. The term I was looking for was elastic. Collisions are 100% elastic. That is, they come in with certain energy, total energy, they go away with the same energy. That's an elastic collision. Okay, characteristics for liquids. Besides having a definite volume and an indefinite shape, They have relatively high densities compared to gases, and they have very low compressibility. What do we mean by that? When you put pressure on a substance, how is it going to reduce its volume? It has to give up space. Right? If there's not much space between the molecules, then it's going to be very low compressible. Right? You have to have that empty space in order to be compressible. And there's not much empty space in liquids, and definitely not in solids. But gases have lots of empty space, so they're easily compressed. Right? We know that from Boyle's law, right? And their density is relatively high. It's in the neighborhood of solids. But one other characteristic we notice with liquids is this phenomenon called surface tension. When you put a liquid in a dish and you take, say a feather, right? Take a feather and just touch it to the surface, you might see the surface of the liquid, especially water. This is true for water. It's the best example. It compresses, but it doesn't wet the feather. The feather just pushes and the water is dented, right? We haven't broken the surface, so to speak. There is tension. There is attractive forces between the molecules at the surface that are a little bit stronger than in the body of the liquid. That's a surface tension. By definition, surface tension is the resistance of that liquid to an increase in surface area. So liquids try to minimize their surface area. So when water droplets are falling, if they're big enough, then they're spherical, right? That's the smallest surface area for a volume of a liquid, is a sphere. Now, of course, if they're smaller and if they're dropping at high velocity, they're going to be kind of teardrop. They're going to be drugged by friction. But that's an opposing force. When ball bearing factories, I think they still work this way. When you form ball bearings from steel, or you're just trying to form steel shot of some kind, or lead shot for that matter, doesn't matter. Make it into a liquid and push it through a sieve of a certain size hole, and it makes droplets. And they fall through this tower of air that's being drafted up, cold air that's being drafted up, and they immediately form into a sphere. That minimizes the surface area. And then when they hit the bottom, they should be solid by then. Let's see. So liquids with large intermolecular forces, these hydrogen bonded liquids, tend to have very high surface tension. So if you, my first degree was in biology, and we went on a field trip one time to our professor's property he had east of Atlanta. And we walked his property, and the course, I think, was invertebrate zoology. So we were looking for spineless creatures, invertebrates. And one of them we found was a water skimmer. So the creek was running pretty fast, but it had to go around this rock, and it formed an eddy, right? A calm region behind the rock. And in that eddy was an insect. It had 6 legs, of course, and they were spread out like this, right? With fingers on the end of his feet. And he was just sitting on top of the water. The reason he could do that, we know that the insect, you can measure it, is denser than water. So how is he able to do that? Well, he's using water tension, surface tension of the water. Right? He spreads his weight out over a large area on these feet, and he rides the surface tension on the surface of the water. And when he saw us coming, you see his feet moving like that, and he just scurried across the surface of the water. So he's taking advantage of that physical property. Capillary action is a consequence of this surface tension. In other words, what you have is with liquids in any size tube. Let's make a big tube first. So we have the liquid here, and we've got forces attracting. So this is a glass tube, and it's water for argument's sake. There are forces that are holding the water molecules together in the liquid. There are also attractive forces between the water and the glass, because glass is essentially silicon dioxide plus some other things. So you have those oxygens sticking out there with their electrons, and they're slightly negative. And then you have water with its positive ends on the hydrogen side, and they're attracted to it. So they're attractive forces that are pulling the water toward the glass. But they're also opposing forces. These are adhesive forces. Unlike materials attracting one another, like materials are cohesive forces. So the cohesive forces are working inside the liquid, and the adhesives are working again with the container. Right? So these forces, and you only have these attractive forces, the cohesive forces are only at the surface around the outer edge. So if you have a big tube, they're not strong enough to lift the water very high or at all. Right? They're essentially balanced out by the cohesive forces and the mass of the water. But if you put a very small tube in there, now you have a lower mass being supported by these cohesive forces, adhesive forces. So the adhesive forces draw the water up the wall, and then the cohesive forces pull them back as far as they can. So you have sort of a stair-step way of thinking of it as the water marches up the tube until those forces balance. The cohesive forces are balanced against the adhesive forces plus the mass of the water. So the capillary will only go so high. So that's why the thinner the capillary, the higher the water. It's a competition. Now, this is what happens in a liquid like water. You get this concave meniscus. Everybody knows that now from lab. But if the cohesive forces are much, much stronger in the liquid than adhesive forces in the liquid with the container, in this case glass, mercury is an example of that. So with mercury, you get a convex meniscus because the cohesive forces are much, much stronger than the adhesive forces. Right? Mercury is not attracted to glass. So that's why in a mercury barometer, if you've ever seen one, they're not too common anymore. But in a mercury barometer that measures air pressure, you'll see the level of mercury rising up against your background scale, and it'll be convex. And you read it at the top of the convex meniscus. This is the concave meniscus for water. Mercury. Water. In the same glass tube. Okay, let's see. So for water, adhesive forces are dominant until the mass of the water drawn up is balanced. This is for capillaries, but the meniscus itself exhibits a predominance of adhesive forces that gives you that curve. See, right against the glass, you see there's some water moving up being attracted to the glass tubing. And that's what gives you the concave meniscus. Another characteristic, physical property of liquids that is attributed to is intermolecular forces, and that's a good thing to remember. All of these characteristics now that we're presenting for the various liquid solids and gases are traceable back to these intermolecular forces. So viscosity is a measure of the resistance to flow. Right? So we know a viscous liquid is one that flows very slowly. There used to be a commercial when I was a kid. I forget whether it was Heinz or some other company. Ketchup, right? Our ketchup flows slower than our competitors' ketchup. So they take the lid off the bottle and turn it upside down. No ketchup comes out, or it comes out slowly in globs. Right? Our ketchup is better because it's more viscous. Viscosity also varies with temperature, because think of what's happening. As you increase the temperature of the liquid, you're also partially weakening those intermolecular bonds, holding those things together, so it flows more easily. So if we say we take honey off the shelf and it slows at a certain rate, if we heat it up in the microwave, or we take, say, pancake syrup, put it in the microwave, heat it up, it's going to flow more freely. It's faster. Or if you stick your honey in the refrigerator and try to pour it out, it just kind of sit there, right? You've reduced the temperature and allowed the intermolecular forces to dominate. So viscosity increases as the intermolecular force increase. Now, there's several ways to measure viscosity. I won't go into those now. It depends on the industry and the material that's being tested. Okay, let's look at solids. Solids can be grouped according to whether or not they have a regular crystalline structure, that is, an ordered structure. These are crystalline solids. Think of things like a diamond. It's a regular arrangement of carbon atoms. In fact, a diamond is, if it has no flaws in it, a diamond is a single molecule of covalently bound carbon atoms in a tetrahedral matrix. Another crystalline solid would be like sodium chloride, right? I don't know if I've asked you this before. You ever dump salt on the table and looked at it with a magnifying glass? No? What you're going to see is cubes, tiny little cubes, all of them, right? No exceptions. They're all cubes. They're cubes because of the arrangement of sodium and chloride ions. They're in that regular cubic structure. That's a crystalline solid. We'll talk more about that in a few minutes. The other type is amorphous solids. Morph means form, right? Structure, form. A in front is the Greek prefix that means not. So they don't have a form. What we mean is they don't have a regular crystalline structure. They're amorphous. In other words, you can't, if you look at one part microscopically, one part of that solid, it's not going to look the same as another part. It may be pure substance, but it won't have the same structure. It has disorder in its structure. Glass is a good example of that. Now, there are many types of glass, so you can create glass that has a crystalline structure. Right? Quartz is like that. But plate glass that we put in the windows is amorphous. In fact, there's one school of thought that says that glass is a supercooled liquid. I don't know. Maybe it works for their research. Let's see. It's just walking around. I forgot to lock the wheels. Okay. So when we look at crystalline solids, since they have a regular structure, we should be able to break them down into the smallest unit that is repeated throughout the structure. That's the unit cell. Now, it doesn't have to be sodium chloride. It's just one example. The unit cell. This is one way of thinking of crystalline solids as a unit cell. This is the smallest repeating unit in the crystal. And when the unit cells are put side by side, they share a plane, at least a plane between them. So the atoms in one unit cell could be shared with the atom, the second unit cell next to them. So you have to think about it in 3 dimensions. The other way to look at solids is in closest packing. Closest packing model. I put it that way, structure. So we're going to look at the unit cell first, and we'll look at the closest packing and see how they relate to one another. That's 2 different ways of looking at the same crystalline structure. So unit cells can come in all different types. These are just 3 of the most common types that are shown here. The top one is in a ball and stick unit cell. So each of the atoms, and it's instructive to think of these in terms of metals, right? So if you have a metal atom like copper or silver or chromium or one of those, and it's pure substance, then it's easier to visualize them as these metals in that structure. But it doesn't have to be. I'm just saying it's easier when you get started with this concept. So the simple cubic unit cell is simply a cube like this, and there's an atom at each corner. Right? And then you can look at it in terms of lattice. And when you look at it in terms of the lattice, then you see that there are several unit cells, and this one would share, say, these 2 would be shared with the next unit cell. These 4, well, actually, these 4 would be shared with the one underneath it, these 4 to the side, so forth and so on. That's what the lattice is doing. And this ball and stick model allows you to see the individual atoms throughout the molecule. But in reality, the space filling model is closer to the way the cell actually exists. In other words, when you have these guys, they're going to be big enough so that they touch one another, right? Like that, throughout the unit cell. So what's the length of this side? Say we have an atom with a radius. The radius of the atom. We talked about atomic radius last semester. Well, the length of that cell, the side of that cell is just 2r. If they're all the same atom, then this is half the way, this is the other half the way. So 2r is the length of the side on that cell. So what's the volume of the cell? It's a cube, a cubed. So 2r cubed is equal to the volume of that unit cell. Okay. That's a simple cube. Now that one's not as common as you might think. What we're trying to do when a solid forms from a liquid, remember stability is equal to lowest energy possible. Right? And to get the lowest energy is not always the simple cubic structure. Sometimes it works better to have a body-centered cube. So we still have the corners occupied like that. But we can use up the empty space in the middle with another atom. Right? So we have the corners are still occupied like the simple cube, but we have a one in the center of the body. Okay. Now, when that happens, the space filling model tells us that these on the corners don't touch. Right. So we need another way, a little geometry, to figure out what this side is. And that's what this document does. This one shows you how that length is calculated. You don't have to know, you don't have to derive this formula. It's just information. But you would have to know, let's see, 4 over the square root of 3 r. 4 over the square root of 3 r times r. So if this is r for each one, then 4 divided by the square root of 3 times r is equal to a. And then you would cube that to get the volume. The other possibility, and one that's reasonably common, is the face-centered cubic. Okay. So we still have the corners with atoms on them. But now instead of 2, 4, 6, 8, instead of putting the any extra atoms in the center of the cube, we put them on the face of the cube. All right, so there, see one up here, should be 6, 2, 4, 6, yeah. 6 sides to a cube, right? So now, we're given examples. Okay, so polonium is an example of simple cubic. Uranium is an example of the body-centered, and gold is an example of the face-centered cubic. So we might say this is body-centered cubic, abbreviations, and face-centered cubic. Okay. Now, I'm not sure, did I do face-centered? I didn't do face. No, I didn't do face-centered. Oh, I got a video. I'm doing it on time. I'm running out of time, of course.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all 3 directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the 3 types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all 3 dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give one particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, and, as you'll see in the next 2 examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell. Zinc sulfide adopts the zinc blend structure, as do the copper-1 halides and several other compounds. If face-centered cubic arrays of zinc ions and sulfide ions approach and interpenetrate slightly offset from each other, each ion becomes surrounded tetrahedrally by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in this slightly expanded view of the zinc blend unit cell.
Okay. Who's the 78%? 74. Okay. So I'm not going to be particular about the last ones talked about. I just want you to see the progression here of space used is higher as you go from simple cube to body center to face center cube. And he also started to draw a connection between the face centered cubic and the closest packing model that we're going to look at in just a few minutes. Okay, I know I'm going to run out of time, so what I'm going to do is this is what I'll always do. If we've got scheduled lecture for a particular day and I run out of time because I'm talking too long, and you have to go, then go ahead. And I'll just keep talking and recording and finish the lecture and post the recording in Brightspace so you can watch it later. Okay. Now we're going to digress just for a minute to describe a procedure that allows us to determine the spacing between atoms in a solid. And again, this is best thought of in terms of metals. It works best for metals. And it's attributed to, I forget the man's name, Bragg and his son, I believe, or his son-in-law. They worked together on this problem, and they came up with this formula. Let's see. Lambda is the wavelength of the light. D is the distance between the layers. And theta is the angle of the X-rays. So when you get a layer of atoms and you got another layer below them, I spread them out like that so we can illustrate it better. Then you got an angle of incidence, right, for the X-rays striking the surface, but they also can go through to the surface below. So you've got the waves hitting the surface and bouncing off, and these bounce off also. And what you get is these waves can interfere with one another. You can get constructive and destructive interference. So the wavelength for X-ray would be very short, obviously. N is the order number. In other words, depending on the angle, you can get interference here that gives you, when we trace it out, right, we have amplitude of the wavelength, amplitude of the signal, and we have scanning theta. So we can scan this way, and the detector out here picks up energy. If it's constructive interference, it'll give you a big peak. So you go out here a certain distance, you may get some jiggles here, and then go like that. And then you keep going on your wavelength, you might get another. Right? So this would be n equals 1, and this would be n equals 2. The order. I used to do this with soils. And you take a soil and you physically separate it down to the smallest particle, silts and clays, and then you put it in a solution and let it settle. And according to Stokes' law, it'll settle faster for the larger particles. Right? So you let it settle a certain amount of time, and then you drop your sucker in there, then you pull out a fraction at this level, and that's your clay fraction. And then you put a drop of it on a slide and let it dry. And clay is if you look at it under a microscope, they're plates. And if you let them settle over time as they evaporate, they'll form these plate layers. Then you can fire X-rays at them and determine something about the internal structure of that clay particle. We can do it for metals too. And this Bragg equation tells you that if you're looking for this peak at that angle and this wavelength, you can tell the distance between those layers. That's what it's saying. Oh, there's a nice picture. And it's all based upon the wave nature of light. Wave nature means you can get constructive and destructive interference. And the Bragg equation takes advantage of that. You can also do it in 3 dimensions, right? I've never done the 3-dimensional X-ray crystallography. It's the same method that was used to elucidate the double helix structure of DNA. Right? X-ray crystallography, that was a real bear to determine. But if you fire X-rays at a 3-dimensional crystalline solid, you'll get, instead of just linear peaks, you'll get a 2-dimensional array. And interpreting that is the real key. Takes a lot of skill. Okay, types of crystalline solids. So we can have amorphous solids, we can have crystalline solids, and the crystalline solids can be broken down into various types. Ionic solids, simple. You just have a lattice of positive and negative charges in that crystal structure. Molecular solids are like ice. Right? You can form the solid from liquid water, and it arranges itself in that hexagonal structure. Or atomic solids that can set them up in one of these ways. Actually, these are not the only types. They're just the most common. Right? There are other different unit cells that can accommodate the different atomic solids. Okay. So let's see, I think I've got this animated. Different forces that are holding these crystalline solids together. Of course, this atomic solid diamond is held together by covalent forces. The ionic solid, of course, is ionic bonding, and the molecular solids, or the metallic solids. Let's see, metallics are slightly different than the molecular, but they do have some similarities. The atomic solids, the metallics we've looked at in terms of this unit cell. Network solids are covalently bound, right? They form one giant molecule, actually. Diamond is the best example. And you can form atomic solids from the noble gases, right? So what forces do they have available? London dispersion. That's it, because they're atoms. Now, one thing that you'll notice is as the atom gets bigger, the London dispersion forces increase in strength, because with a larger volume, you have more opportunity for electrons to distribute themselves unevenly over a larger volume. So you have also the opportunity for stronger London dispersion forces. And you'll see that in their melting points. Right? The melting point for helium is 4K. Right? It's the coldest liquid that we can make in bulk. It's liquid helium. And the neon melts at a higher temperature, argon, krypton, xenon, increasing higher temperatures as you go down in that group. Okay. The animations didn't come out of your textbook, but the table did. Now let's look at the closest packing model. I've got another video coming up in just a minute. The closest packing model approach is to take first linear arrangements of atoms or molecules, and then form them into two-dimensional structure, and then put the two-dimensional structures together into three dimensionals in different ways. And in order for this to work, we have to consider the molecules or atoms in this arrangement as solid spheres. That's one of the postulates that's required for this to work. And we pack them in layers. Okay, when I start this video, start to tune your ear to an Indian accent. Not Native American, I'm talking about India. Right? So it may be a little difficult at first, but her English is pretty good. It's just it takes a fine tuning of your senses.
The three-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps. Close packing of spheres in one dimension. In one-dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, in one-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of one-dimensionally closed packed spheres, one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So, the coordination number is 4. If we call the first row as A-type row, the second row being exactly same as the first row, so it is also called as A-type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AAA type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A-type, then as the second row is different from the first row, it can be called as B-type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the 4th layer, we will observe that the 4th row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as ABAB type of arrangement or hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, the coordination number is 6. If we call the first layer as A type, and since all the layers are also of the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice, and its unit cell is primitive cubic unit cell. Dimensional close packing from 2-dimensional hexagonal closed pack layers. The 3-dimensional hexagonal closed pack structure can be obtained by placing 2-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a 2-dimensional hexagonal closed packed layer A. Notice this layer has triangular voids. Place a similar closed packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are 2 types of voids: tetrahedron voids denoted by T, octahedron voids denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T, since a tetrahedron is formed by joining the centers of the 4 surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O, since an octahedron is formed by joining the centers of the 6 surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in two ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we can call the first layer as A type and the second layer as B type, then the third layer will also be A type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal close packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A type and the second layer as B type, then this third layer will be C type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close-packed CCP or face-centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12.
Okay, that's a lot to digest. We see a relationship here with the square close packing. This gives you the simple cubic, and the ABCA gives you the cubic closest packing. I didn't see any relationship there that I could draw between this and the body-centered cube. So the AB is formed by covering only tetrahedral chords. And the ABCA covers both, alternating. Covers both tetrahedral and octahedral chords. That's the difference. Now, this arrangement doesn't cover any voids. Yeah. Oh, yeah, sure. Okay. The AB results in hexagonal closest packing. Check them out. Yeah, okay. That's consistent with the slides. And the ABCA is face-centered cubic. This one. Cubic closest packing. So hexagonal closest packing is face. Well, this is also, it goes by two different names, right? Hexagonal closest packing gives you face-centered cube. Face-centered cubic is also cubic closest packing. Hexagonal, this is HCP also. So that's where it can get confusing. Actually, hexagonal closest packing and cubic closest packing, ABCA versus ABAB. Okay, so what they're saying is, and here's a clue, they both have coordination number 12. So hexagonal closest packing is here. That's there. Versus cubic closest packing. And they both give you face-centered cubic. Yeah, they both give you face-centered cubic. Let's see, coordination number, we talked about that already. Now the net number of spheres, this is important if we're going to do calculations that determine densities, calculated densities of metals in particular. You need to know both the mass and the volume to do the density. So the volume of the sphere is going to be dependent on how many atoms. Well, the calculation is going to be dependent on how many atoms are part of the sphere. In this case, you've got one atom. Cubic closest packing gives you one atom per unit cell. This one gives you two, and the face-centered cubic gives you four. Yeah, if you have to go ahead, and I'll keep recording. And we'll meet again on Thursday. Okay. So there, and they left out the body-centered cubic, which is two atoms. All right. The length on the edge, the simple cubic is the easiest one. It's just 2 times the radius of the atom. The face-centered cubic, here we go. The face-centered cubic length of the edge, this A, is equal to the square root of 8 times R. I don't have a document to show you how to calculate that one. It's some geometry. Okay. And then there's the body-centered cubic, R times 4 over square root of 3. All right, so if we were to use that information to calculate the density of silver, if we know that the unit cell edge is 409 picometers, and that would have been calculated from the radius of the silver atom put into this, face-centered cubic. Put into this formula would give you the edge, and the edge has already been given to you as 409 picometers. Then calculate the density of the silver metal. The way to solve this problem is to work backwards. If you're asked to do the density, you go to the density formula and say, what do I need? And what am I given? So density is equal to mass per unit volume. You need to know the volume of the unit cell, you need to know how many atoms of silver are in that unit cell, right? Cubic closest packing. Cubic closest packing. This one, right? No, face-centered cubic, excuse me. Face-centered cubic. Here we go. This one. Face-centered cubic means that we would have calculated, the A is equal to 409 picometers. But you also need to know the units of measure. For solids, when we talk about densities, you remember the units of measure? Grams per cubic centimeter. So you need the volume in cubic centimeters, not in picometers. And you need grams if you know how many atoms are in that unit cell. How many atoms are in this unit cell? I erased it. So this has one, that says 2, 4. 4 atoms per cell. Okay. So we can find out, if we have 4 atoms per cell, we can find out what's the mass of silver in that unit cell, right? If we have 6.022 times 10 to the 23rd atoms is 1 mole, is what's the mass of 1 mole of silver? 107.87. 107.87 grams. Right. Yeah, so that gives us the mass per unit cell. Now we have the mass is done. What we need now is the volume. We just do this calculation. Now we need the volume. So if we have 409 picometers, the volume is going to be 409 picometers cubed. But we have to do our unit conversions, right? What's a picometer? Picometer here, meters here. Picometer is 10 to the minus 12 meters. Right? Nanometer is 10 to the minus 9. Picometer is 10 to the minus 12. So what do you do when you've got this factor out here? You've got the conversion factor here for linear. You just cube it. Remember that? Way back chapter 1 and 2. Okay, now we have cubic meters, but we need centimeters, right? So if we've got meters to cancel the meters and centimeters, we have 100 centimeters per meter. We need to cube that one too. So now that gives us the volume in cubic centimeters. So once we get this value and that value, plug it in the formula, and that's what the next animation does. 10.5 grams per cubic centimeter should be the result. We're going to calculate this as 6.84 times 10 to the minus 23rd cubic centimeters. Okay. And the mass is 4 atoms, okay, times that. And we put those values together in the quotient, and you should end up with 10.5 grams per cubic centimeter. So the given value, the measured value of the density of silver is 10.5 grams per cubic centimeter, and the calculated value is also. That's good agreement. So I'm already past, so you guys going to stick around? You don't have to, but you can. Okay, bonding models for metals. Right, the earliest model for explaining how metals are bonded was called the electron sieve. We knew that metals had some fairly loosely held valence electrons. That's why metals form, when they form ions, they always form cations, because those outer layer of electrons are not very tightly held. So if we extend that to pure metal, then we see those valence electrons are out here easily moving from one center to another. That's the electron C model. And that's what it would look like in an artist rendition. But that wasn't very satisfactory. It was just a starting point. What we needed was some way to actually calculate the amount of energy required to move the electron from one atom to the next. And for that, the molecular orbital model was much, much superior, right? And we've experienced some of that with diatomics at the end of last semester, the molecular orbital model. In this case, the entire structure is viewed as a single molecule, and a new set of molecular orbitals is substituted for the atomic orbitals that go into the metal structure. And what we end up with, if we only have two metal atoms, we get this energy difference between the two. If we go to 4, then the gap starts to decrease. And when we get to a whole mole of atoms, which would be, for silver, would be 108 grams of silver, you get virtually a continuous layering of molecular orbitals. So it's very easy to move from one molecular orbital to the next. The band gap is very, very small. That's why metals are very good conductors of electricity and heat. Another way of thinking of this is when you get your orbitals set up and the atoms next to one another, the highest orbital is the highest occupied molecular orbital, or the HOMO. The highest occupied molecular orbital is here, and the lowest unoccupied molecular orbital is here. What's the gap between these two? The energy gap here. If it's very small, then it just takes a little bit of energy to move an electron up to here, and from there it can move to the next atom. So that gap is the indicator of how good an electrical conductor or heat conductor the metal is. In fact, silver is the best heat and electrical conductor in the periodic table. It has that smallest gap between the HOMO and the LUMO. That's why when if you ever build a computer and you got your CPU sitting on the motherboard and you want to put your cooling device on top of it, because it generates a lot of heat, you need to keep it cool. What you'll do is you'll get this paste that's an emulsion of silver. And you squeeze that paste out there and spread it on the top of your CPU. And then you put usually a fan with a heat pipes on it that go to the fan, and you stick that on the top. It's a very good conductor of heat away from your CPU into the cooling unit. How do we form alloys? What is an alloy? Alloy is a solution of metals and other things. So we can subdivide alloys into two types. The substitutional alloy, where you actually remove one of the mother metal's atoms and replace it with a different one. A good example of that is brass. You have mostly copper, right? And then you put some nickel in there, and the nickel substitutes for some of the coppers. Okay. The other type of alloy is interstitial alloy, and the best example of that is steel, where you have iron atoms that are the base for steel, and then you put carbon in the gaps, in those voids. Carbon goes in here in a fraction of a percent. That's an interstitial alloy. So there are your examples: brass versus steel. Now, different types of stainless steel are a combination of interstitial and substitutional, right? The stainless steel will have chromium, primarily chromium substituted for some of those iron atoms. Different structures of carbon. These are called not alloys, but I forgot the term for it now. Maybe it'll come to me. It's the same material, right? It's still carbon, but diamond is a different structure than graphite. Notice graphite is covalently bound hexagonals in a plate, and then weak intermolecular bonds between the layers. That's why graphite is often used as a dry lubricant, because it allows one object to press against the other one with this graphite between it, and it's very slick. Those layers move. So we used to take graphite, my motorcycle cables, and squirt it down the cable guides. It would lubricate your cable guides, and it wasn't wet, so it wouldn't attract dust. I wish I could remember what was going to bug me. All right. One thing we'll notice is the band gap between the HOMOs and the LUMOs for diamond is very large. So that means that diamond is going to be a very poor conductor of electricity and a poor conductor of heat. In fact, jewelers will determine the authenticity of a gem. If it's claimed to be a diamond, they have a device that just put the device on it and see what's the thermal conductivity of that stone. And if it's below a certain level, it's not diamond. It has to be, if it's above a certain level, it's not diamond. It has to be below a certain level because diamond is a very poor conductor. Right? So my wife got a stone, it's like maybe 2 carats. It's supposed to be a tanzanite. Her friend thought it was a tanzanite and sent it to her. And we showed it, we took it to the jeweler and showed it off and says, and look at our tanzanite. They said, no, that's a beautiful blue diamond. I said, what? It's supposed to be a tanzanite. So they got their device out, put it on there. Sure enough, it's a diamond. So her friend made a mistake and sent us a diamond instead. And 2 carat blue diamond is lots of money. So we contacted her friend and he said, keep it. Got more money than knows what to do with. Metals have a tendency to be a very narrow gap between the HOMO and the LUMO, whereas network solids like diamond have very wide gaps. When we look at graphite, I think we talked about the structure of benzene at the end of the last semester, where we have overlapping p orbitals, right? And they form this donut. Well, if you hook those together in overlapping hexagons, now you can get the structure for graphite and the different layers of graphite. So this layer is going to be very tightly covalently bound. This one's tightly covalently bound, but the difference, the attraction between them is purely van der Waals. Van der Waals is another way of putting it. London dispersions. That's why graphite, those layers slide past each other very easily. Ceramics are solids that are essentially operationally defined. In other words, they can be almost anything, and they're defined by their characteristics. They're usually non-metallic metals that are materials that are strong, very strong, but brittle. In other words, they can undergo extreme compression, like concrete, right? Pure concrete or stone can only span a distance that's relatively narrow. That's why when you look at Stonehenge, reconstructions of Stonehenge, the distance between the pillars are no more than, say, 10 feet or so. And you have this huge capstone across there. It has to be extremely thick. If it wasn't, it would break under its own weight because it's very brittle. That's characteristic of ceramics. They're brittle. But they're very good. They're very resistant to heat and attack by chemicals. They're often used in metalworking. In other words, when you work metals in a furnace, it may be lined with these ceramic bricks that are specially constructed to withstand thousands of degrees of temperature. They're typically made from clays. Clays are essentially silicates or aluminosilicates. And they're hardened by firing. So if you've ever seen videos of brick factory, the last video I saw was a brick factory in Georgia. So they get that nice Georgia red clay, find a big deposit of that, and they form it into bricks. And before it goes into the oven, right, you can take that brick and just break it apart. But once it goes through the oven and gets fired, it goes through what's called pozzolanic reaction. The crystal structure radically changes and forms a ceramic. And from that point on, it's very strong. Some other types of solids, semiconductors. Semiconductors are based upon a base material or the host crystal. And most of the semiconductors now commercially available are based upon silicon. So you need pure silicon in wafers. And if you've ever seen a video of the production of one of these ingots of pure silicon, they grow them. They're about that big around and about 12 feet long. And they pull them out of the growth chamber, and they have to be as pure as possible. And then they take that, they clean it, and then they slice it into wafers. And then upon that silicon base, they build up the layers of circuitry. Well, one way that they can modify the behavior of silicon is to substitute. In one respect, it's kind of an alloy. They substitute for that silicon matrix some other element. Silicon knows where silicon is, right? It's below carbon. So anything to the right of silicon is going to have extra electrons. So if we say we put phosphorus in there or arsenic, let's put arsenic in here. Arsenic is going to have one extra electron, right, which can move. That's known as an N-type semiconductor, for negative. Right? If, on the other hand, we form, instead of arsenic, we put something on the left of arsenic, it's going to be deficient. So if we put, boron, we put boron in here, it's going to be deficient in an electron. So it's going to be positive. That's a P-type semiconductor. Now, a semiconductor is just what it says. It's not a conductor, and it's not an insulator. It's somewhere in between. So it will conduct electricity under the right circumstances. Now, how it does it depends on whether it's a P-type or an N-type. If it's an N-type, then when you put a voltage force, the electron jumps. Right? If you put a force on the P-type, then the hole jumps. That's the way they think of it. The hole jumps. Actually, an electron jumps from here over here, and that leaves a hole over here. So the hole moves this way, and the electron moves that way. And the nature of the semiconductor is based upon that gap between the HOMO and the LUMO. So the difference between the HOMO and the LUMO in a semiconductor is greater than it is for a metal, but less than it is for a non-metal. Okay, so that makes the silicon, the doped silicon, slightly more conductive than it was as pure silicon. Okay, there's artist rendition. Okay. We haven't talked a lot about ionic solids, except to say that sodium chloride is an example of an ionic solid. And it's a network of positives and negative charges. And characteristics of the ionic solid is that it's very high melting point. In other words, you can get sodium chloride into a liquid state, but you need a couple of thousand degrees temperature, in which case it becomes conductive now because the ions can move. Now, what is actually responsible in the difference in melting points among ionic solids has to do with those two factors I mentioned earlier: the size of the charge difference and the distance between the ions. So you get a stronger attractive force if the charge difference is greater. So sodium chloride is a charge difference of one positive, one negative. Magnesium oxide is a charge difference of two positives and two negatives. So based on that, it should be a stronger attractive force or a higher melting point. In addition, the sodium and chloride ions are big, 280 picometers between their centers, whereas the magnesium and oxygen difference between the charges is 212 picometers. So you got both of those factors leading to a higher melting point for magnesium oxide than for sodium chloride. Okay. Now these are remember the discussion from that video of the voids. If you're only looking at two dimensions and you get three atoms together, you're going to have a triangular void in between them. These holes are too small for the cations to be fit into. Remember, when you make an anion, you're adding electrons, so it makes it bigger. When you make a cation, you're removing electrons, makes it smaller. So if we're going to make an ionic solid and we want to fit cations in the void, then they have to be small enough to fit in there. And for most binary ionic crystals, these trigonal holes are too small for the cations. So we don't find that in things like sodium chloride. With tetrahedral holes, now we're into 3 dimensions. With tetrahedral holes, you've got one atom covering a trigonal void. Now it's a tetrahedral void in 3 dimensions. And in that case, you can fit the zinc into that tetrahedral void. So that in the earlier video where it was the zinc blend, this is where the zinc goes. It goes into the tetrahedral void. An octahedral void from a hexagonal closest packing gives you a little more space. I think the octahedral is a larger void than the tetrahedral void. Okay, so I don't know why I keep this slide in here. The trigonal hole is smaller than the tetrahedral and smaller than the octahedral. You're comparing apples and oranges here because the trigonal void is 2-dimensional and the tetrahedral and octahedral are 3-dimensional. So it is what it is. All right, this came straight out of your textbook, and it organizes all the information that we've covered so far. And so I'm not going to stop here. Now we're going to go away. We're going to leave solids for now and go to liquids. And we're still talking about characteristics, physical properties of substances based upon their intermolecular attractions. When you put a liquid in a closed vessel, the first thing that happens is that atoms from the liquid surface can escape into the vapor phase. Right? And that's all that happens in the beginning. But once you build up a certain number of atoms or molecules from the liquid into the gaseous phase, now you have the opportunity for some of them to return to the liquid phase. So you get this equilibrium set up eventually between evaporation and condensation. And when that happens, it's characteristic of the material, the liquid. When that happens, if the vessel is closed, you build up a pressure. That's the normal vapor pressure for that liquid. Well, the normal vapor pressure occurs at 25 degrees Celsius. This is another way of looking at it. Over time, you see the rate of condensation is 0 in the beginning. The rate of evaporation is constant. But eventually you get the rate of condensation meeting the rate of evaporation, and at that point you have an equilibrium set up. This is a phase change equilibrium. It looks static, but it's not. And this vapor pressure is the point at which you have reached equilibrium. There's no apparent net macroscopic change in the volume of the liquid phase. Okay, what's the vapor pressure of water at 100 degrees C? It's 1 atmosphere, because that's the boiling point. This little slide shows different materials in that space in a barometer. And the point is to show you what the vapor pressure is at a given temperature. This would be at normal room temperature, 25 degrees C. And the water vapor in the top forces the mercury down by just a little bit, right? 760 minus 736, which would be what? 24 torr would be the vapor pressure for water. For alcohol, for ethanol, it has a higher vapor pressure because it has lower intermolecular attractions. It only has one OH group for attractions, whereas water has two. So you get a vapor pressure for ethanol of, let's see, 65, right? Oh, all I have to do is read the slide, right? I was trying to calculate in my head. 65 torr is the vapor pressure. But for dimethyl ether, which has no dipole moment, to useful dipole moment, it only has London dispersion forces, then its vapor pressure is 545 torr. Enormous, right? There's not much holding it in the liquid phase, so it's easier to evaporate. So as the intermolecular force attractions go down, the vapor pressure goes up. That's the one physical property we've discussed so far that is inverse. The rest of them are direct. Okay. Let's see. So we also know that vapor pressure changes with temperature. And this is a graph of the change in vapor pressure for water in the bottom, ethanol in the middle, diethyl ether on the top. So when it reaches the temperature at which the vapor pressure reaches 760 torr atmospheric pressure, that's the boiling point. So we find that happening for 100 degrees for water 78 degrees for ethanol, and 35 degrees for diethyl ether. All right, you don't have to know how to do this. This particular formula is used to graph information, boiling points, and vapor pressures, temperature versus vapor pressure for any given substance can be put into this formula and calculate the heat of vaporization. In other words, when you go from, say, liquid water to gaseous water, you have an amount of heat that has to be added per mole. That's the heat of vaporization. And it can be determined from this plot. Notice that the natural log of the vapor pressure is plotted against the inverse of the temperature. And of course, the temperature has to be in Kelvin. And the slope of the line is a negative delta H over R. So if we go to the next slide, we see that plotted here. Okay, so all you need to do from that plot, plotting the vapor pressure versus temperature as natural log versus the inverse of temperature, and the slope of that line can be fit into that part of the formula, delta H, negative delta H over R, will give you the, you can solve for the vapor pressure. Heat of vaporization. And an easier way to do it is that bottom formula, where you have the vapor pressure at two different temperatures, and then you put the two different temperatures into the formula, and you can come out calculating your heat of vaporization. Either way works. This is the Clausius-Clapeyron equation. And we use R as the one with joules, 8.3145, not the one with liter atmospheres. So if we go in here and take this information, 25 vapor pressure of water at 25 degrees is 23.8 torr, and the heat of vaporization is given to you, what's the vapor pressure of water at 65? Right? It's just like any formula. If you have all the variables have numbers, then the one variable that doesn't have a value, you can solve for it. And that's what this procedure does. So we find out that if we increase the temperature to 65 degrees, now the vapor pressure is 195 torr instead of 23.8. Okay. I should be getting close to the end of this chapter.
You're on the last page.
Okay. So this is a heating curve for water. Notice what happens when we plot temperature against added heat. Added heat over time. And as we heat up the solid, the temperature increases as we add heat. Right? And once we get to a temperature, the melting point of that solid, we have solid here. Here we have solid and liquid together. So what's happening? We're adding heat to the solid, and it's causing the molecules to vibrate. That's it, but they're still stuck in their positions. They're just more energetic. Once we've converted some of that to liquid, now the energy that we put into it is breaking the bonds between the intermolecular bonds between the solid, and now the heat goes in and the temperature doesn't increase anymore. So that's why it's flat. This is at the melting point. Okay? Once we've converted all that solid into liquid, now we're adding energy to vibrate the liquid some more. and its temperature starts to increase until it reaches the boiling point. Now it flattens out again. At this point, you have nothing but liquid. Here you have liquid and gas. Now we're adding energy, and it's not going into increasing the temperature of the liquid. Now it's going into breaking all the bonds of the liquids to form gas. And once you've got all gas, now you can start increasing the temperature again. Okay, so that's typical of a solid liquid gas transition. As long as you've got two phases together, the temperature is going to be stable. That's why when we did labs and I said, you're going to measure the temperature, the melting point of water, make sure you have solid and liquid together. It's stable at that temperature as long as you've got both of them together. Okay. Which would you predict to be larger for a given substance, the heat of vaporization or the heat of fusion? Well, what does that mean? Well, here's the heat of vaporization right here. Vaporization. This is the heat of fusion, going from solid to liquid or liquid to solid. Fusion is a conversion from liquid to solid, but it's the same, we just reverse the sign. Okay. So which would be the larger value? Here, all you've got to do is weaken the bonds so that the molecules can flow past each other. It takes a little bit of energy. But when you have to break the bonds completely to where they're independent players now, that takes a whole lot of energy. So the heat of vaporization is always larger than the heat of fusion. Okay. That's not the only way to represent the different phases. Another way is a phase diagram. And in a phase diagram, we are plotting temperature against pressure. Now, these phase diagrams can be extremely complex. So we're going to use a very simple example. Water. So as we increase the temperature, and we can also increase the pressure, we notice that as the pressure increases, it takes more temperature for the phase change. And at this point, which is called the triple point, we have all three phases together, solid, liquid, and gas. But for water, and this is called the phase change line, I believe. This is going from, there's gas, this is solid, and this is liquid. Then we go out here like this. So any combination of pressure and temperature that puts you on the line means that you have both of those phases together. So at this combination of pressure and temperature, we have liquid and gas together. At this combination of temperature and pressure, we have solid and liquid together. And at this combination of temperature and pressure, we have solid and gas. And at this singular combination of pressure and temperature, you have all three phases, solid, liquid, and gas together. Now out here, there's a point. At this pressure, this temperature, and beyond that, in this region, is the critical region. Critical region. And this is the critical point. At that, anything above that pressure at that temperature, or increasing pressure at that, or increasing temperature at that pressure, will put you in this region. And in that region, you still have a fluid, but you don't see the difference between liquid and gas. That phase disappears. You don't see it anymore. And every pure substance has a critical point and a triple point. And these are, oh, phase equilibrium lines. That's what these are. So how would we use this information? Well, if we hold the pressure constant, say the pressure is down here, and we increase the temperature at that pressure, then we're going to go from solid to gas. That's sublimation. Right? Or if we hold the temperature constant and we increase the pressure, we're going to go from gas to solid. That's deposition. Okay? So you can do that across any one of these lines. Right? Hold one of them constant, let the other one increase or decrease and cross that line. And let's see, this would be sublimation. This would be deposition. What is solid to liquid would be, at that pressure, this would be melting. And this would be freezing. If we went this way, from liquid to gas, this would be vaporization. And if we went from gas to liquid, say we were going this direction, gas to liquid would be condensation. Okay, most materials show a positive slope on this line, the solid liquid equilibrium line. Water is different. Water has a negative slope. So in other words, if we say at this temperature, start increasing the pressure, I go from gas to solid and back to liquid. Right? Most substances go from, as you increase the pressure, go from gas to liquid to solid. But water's different. This is an example of carbon dioxide. It is more well behaved. In other words, the solid liquid equilibrium line is positive slope. And I don't have time to talk a whole lot about that. This slide illustrates what I just showed you with water. Okay, intermolecular forces. As they increase, what happens to each of the following? As we increase the intermolecular forces, we get an increase in boiling point. We get an increase in viscosity. We get an increase in surface tension. We get an increase in the enthalpy of fusion, heat of fusion. We get an increase in freezing point. And we get a decrease in vapor pressure. And the heat of vaporization also increases. So the only one that decreases that's inversely proportional to intermolecular forces is vapor pressure. All right.